Okay, so here is our second of two lessons on exponential and log functions. And we're going to be talking about the natural base for both natural exponential base and natural log base, and also go through some rules of logarithms. Okay. But to get to that, let's pick up that problem we were working on. We had that model of infectious spread, uh, y equals 2 to the power t, and we asked how long, how many weeks would we expect it to take to get to 10,000. So we wanted to know what value of t uh, makes 2 to the t equal to 10,000. And we sort of asserted that the answer to that was given by log 2, 10,000. Now that we've defined what a logarithm is, and that we know that it's a function, we can just apply that function to both sides of this equation. Okay, so what we're going to do here is take log base 2 of sides. So we'll get the log base 2 of 2 to the t power is equal to the log base 2 of 10,000. And here, oh, look, I said that those definitions of logarithms were just going to be showing up all over the place. I guess this is the one that we were calling the D2 definition, that if you first raise a base to a power and then take the log for that base, you get back to t. Okay, so that this equals the log base 2 definition of log. Okay, that's great. Problem is, my calculator can't tell me what the log base 2 log rather of 10,000 is. I have what's called a natural log button, and sometimes calculators will might have another one, but typically that's the only one that you have. No problem. We don't need to keep track of all of these bases in the way that you might think. There is a natural base for both the exponential and the log functions, and so that's what we talk about. That's what I want to talk about right now. We really need one base. Okay, the natural exponential base is the irrationals. It's one of those numbers that never settles into a pattern, never ends, that goes by e. It starts out 2.71828, on and on and on. It's sometimes called Euler's constant. Euler spelled the German way, so it's EULER. Maybe that's what the E stands for. And this is the natural base for both exponents and log functions. And you might be thinking, why is such a crazy number the natural base? And I keep saying, wait till we've learned a little bit of calculus and all of this will become clearer, but that is the answer here. Once we start understanding the calculus properties of exponential functions, you will see why this base is kind of the natural one. Okay. So with that number as the base, then we have also the natural log function, which would be a log base e, but everybody writes this as ln, natural log. All right. You can translate any base into the natural bases, and again, you're just using those definitions of logarithms. Okay, so we started off with our function that was not base e, it was base 2. And remember that 2 actually came from the problem we were studying. We were saying that the 2 was the number of people infected by a single person who was contagious. Okay, so that 2 is coming from the world. So if that's coming from the world, how do we translate that into something involving E? Well, we use our D1 definition of logarithms, which let's remind ourselves what that says. It's that x equals b to the log base b of x. Okay, remember that? It's kind of one of the high points of the last lesson. What does that mean when the base is e? X equals e to the natural log x. So again, all these things are really saying here is they're just reminding us of the fact that these are inverse functions. And so what I'm going to do is I'm going to say, well, if that's true for any x, it's true for 2. So I'm going to rewrite that 2 here, make my y a little bit thicker, as e to the log 2 to the t power. Okay, so just that's where the rabbit goes in the hat. So let's really pay attention to here. All I've done is I've taken this 2, and I said it's just the same thing as e raised to the log 2 power. Using this definition of logarithm. If I take the log of 2 and then raise e to the power log of 2, I get back 2. Why would I want to do that? I would want to do that because I'm translating this problem that's got kind of an inconvenient base to it to the natural base. And then using the law of exponents, I might go ahead and rewrite this as e to the power ln2 times t. Okay, and if you don't remember why this works, you might want to go back to lesson 1b, the rules of exponents. This is, I'm just applying the rule that says if you have a base, a raised to the power m, and then that raised to the nth power, the result is a to the m times n power. Okay, so that's one of our rule of exponents. Okay, so step back. I'm trying to find the value of t that, according to this model with base 2 here, gives us 10,000 cases. How long is it going to take this model of each person infecting 2 within a week? How long is it going to take us to get to 10,000 cases? And I've rewritten that model. So it's not base 2, but it's base e. And I've done it just by having the logarithm of 2 up here in the exponent. So what I'm just going to assert, and then I'll do, is that now I can solve this the same way, but because I'm taking natural logs, I'll be able to actually get a numeric answer here. Okay. So give myself a new page. Y equals e to the log 2t power. Again, I'm going to take the log of both sides, but now because we're working with a base e, I'm going to take natural logs. Okay, so actually, before I do that, let me put in the value of y I care about. Let's get back to the problem that we're solving. This is the general function. We had a specific question, which was, when do we get to 10,000 cases? So putting in 10,000 is the y value we care about here. Still e to the log 2, and t is what we want to know. But now I'm going to do that step. I'm going to take the natural log on both sides. So log of 10,000 against the natural log here is equal to the natural log of e to the ln2 times t. Okay, so that is just going to be ln2 times t. 10,000. So just as we did when the 2 was in the base, when you take the log of e raised to something because they're inverse functions. The log and the e cancel each other out, and what you get is the thing that you're raising e to. But now we're raising e to more complicated power. It's t times the log of 2, so no problem. That's just that's the equivalent of the x here in the claim that the log of e to the x is x. Okay, so same logic that we've been doing multiple times. Yeah. So we say that t is the log of 10,000 divided by the natural log of 2. I do have a natural log button on my calculator. There's a natural log function in Excel. Any programming package you want to use will have natural log, and you can actually get a numeric answer. And the answer that I got, where did it go? Here it is. It's around 13.288. Take it out more decimals if you want. Okay, so this is the weeks to get to 10,000 cases. And again, that sort of sounds right, that we knew it was going to be more than 12, because at 12 weeks we had around 4,000 cases, less than 20, because by 20 weeks we had over 1 million and closer to 12. All right. So this process of using logarithms to solve functions involving exponentials, that in and of itself is a good use of logarithms. You want to be able to do that. But logarithms end up coming in handy for all sorts of reasons, so much so that I want to just sort of go through a couple of algebraic rules that they have, or almost I might even say because of these rules is the reason why they come in handy. So for the very last thing I want to talk about in this lesson, what are some rules of logs? I'm going to write them in terms of natural log, but you're going to see that they just come right from the rules of exponents, so they would apply to any base. Okay, so rule 1 is the log of u times v is the log of u plus the log of v. So sometimes we might say the log of the product is the sum of the logs here. Okay, that seems pretty weird. Not kind of a natural thing that you'd expect. So let's check this out. Is this really true? I'm going to show this is true. So we're going to start the log of this product here, and we're going to substitute for both u and v. We're going to use the definition of the log to write them in a weird way. Okay, still the log here. I'm going to write u as e to the log u power. Still using that definition. I can do that. Okay, and I'm going to write v as e to the log v. Okay, so just using the definition of log to rewrite v. Fine. So keeping going here, just looking at what I've got in the parentheses. Oh, look what I've got here. I've got the same base multiplied raised to different exponents. I'm going to use the rule of exponents here. That is e to the log u plus log v powered by rules of exponents. A to the n times a to the m is a to the n plus m. Okay, good. Now, I'm going to use the definition of logarithm in reverse. I'm going to say, oh, look, I'm taking the log of a thing that is e raised to that power. So the log and the exponent cancel each other out. If you want to think about it that way, they're inverse functions of each other. And this is indeed just log u plus v. What we're thinking about here is again, so let this be, just think about this as x. I've got the log of e to the x. That is equal to x. Okay. I always think this is such a kind of a cute little derivation. But the rule comes in super handy. Okay? What the rule tells us is if we have the log of something that's a product, we can break it up into the sum of the logs of the factors. That gives us all sorts of possibilities. So let's go on. I think I'm not going to derive the other rules, so I'll just, I would like to write all the rules together here. So of logs, we just showed rule 1, that's log of u times v equals log of u plus log of v. We've got a kind of a similar thing for quotient. The log of u divided by v is the log of u minus the log of v. It's almost the same process. The log of u to the power a is a times the log of u. And rule 4, the log of 1 over u equals the negative u. Okay. So we'll be using these rules later in Math Camp. We'll be using them in 200A. And the kind of contexts in which they come up, two things, sometimes they even occur together. So sometimes we will find ourselves wanting to take logs, when you take a problem that doesn't have logs in it, and apply the log function, which we can do because it's a function, and you apply it to both sides of an equation, you're not changing anything. We will do it specifically because it's easier to deal with sums than it is to deal with products, or easier to deal with differences than it is to deal with quotients. The other reason why we might find ourselves wanting to take logs is just as exponential functions can take kind of like normal small to medium numbers and all of a sudden assign really large values to them, like with the exponential growth with t equals 20, we were getting over 1 million. Because the logs are the inverse of that, logs take crazy big numbers and bring them down to manageable sizes. So you could find yourself with numbers that are actually too big for your computer to work with. If you take the logs, they'll be simpler. And again, it's hard for our brains to process how much this happens. So for example, if you want to take the log of 1 trillion, that's 10 to the 12th power. It's around 27 point something, 27.6. Okay, so that in and of itself can be an advantage. And that might sound kind of esoteric now, but in 200A, we're going to see exactly that problem come up in a pretty mundane context. Okay.